We will continue our discussion on various notions related to boundedness in the system of real numbers. Let us quickly recall the definitions that we made in our previous session. Remember that a subset of R, which is we call as A, is said to be bounded above, provided there exists a real number B such that whatever element we choose from the set A that is less than or equal to B. That is precisely the exact definition is A subset of R is bounded above if there exists B belongs to R such that for every choice of A from A, we have A less than or equal to B. And in this case, we call B as an upper bound for A. There can be some confusion regarding the notion of upper bound. For example, to clarify these things, we consider the set of all possible marks a student can probably score in an examination where the maximum is 100. So suppose that A is equal to set of all marks in a paper that varies from 0 to 100. So obviously a student can score a maximum of 100 and therefore 100 is an upper bound for this set. And what about 101, 101? 101 is also an upper bound for this set. There can be some confusion because we may be thinking that the student can never reach 101 and why we are taking 101 as an upper bound. See, the definition of upper bound simply says that whatever element we are choosing from that particular set, it should not exceed that upper bound. Therefore, if you take the number 101, the maximum mark that a student can score is 100, and therefore it cannot definitely exceed 101. Therefore, 101 is an upper bound for A. The same way, 102 is an upper bound, and in fact, 100.5 is an upper bound. Anything above 100 is an upper bound. And what about lower bound? We can see that 0 is a lower bound for this set. And of course, minus 1 is also a lower bound. Now, the confusion once again is that why are we taking a negative number? Because mark cannot be negative. We didn't actually say that mark is going to be negative. What we said is mark cannot fall below minus 1. That's the only meaning of saying that minus 1 is a lower bound. So it's a lower bound means that elements in A cannot fall below that lower bound. Therefore, minus 1 is a lower bound, and in fact, every negative number after 0, including 0 is also there. Every negative number after 0, below 0, is going to be a lower bound. What about supremum of this set? We can see that 100 is an upper bound for this set because no mark can cross 100, and not only that, any other upper bound has to be greater than or equal to 100, and therefore 100 is the supremum of this set. And we can also see that 0 is the infimum of this set. Not only that, maximum of marks in this set we can found to be equal to 100, and therefore 100 is the maximum and 0 is the minimum. These are all quick facts that we have to revise from the notions of boundedness that we have so far learned. Now we are going to introduce a very important result in real analysis. That result actually makes the real number system somewhat special compared to the system of rational numbers. That particular result is actually an axiom. In mathematics, an axiom is a statement that does not require a proof. It does not require a proof means that it is supposed to be, not only it is supposed to be, it is very obvious and does not actually require a proof, and actually it cannot be proved from any of the existing results. Therefore, can we call anything as an axiom that cannot be proved? No, that's not the case. An axiom is a statement that is in consistency with all the existing results in mathematics, And not only that, it should not create any confusion with any other existing axioms. So axiom is an elementary result that cannot be derived from any other existing results in mathematics. Now we are going to state an axiom which is very special to the set of all real numbers. The axiom simply says that whatever non-empty subset of real numbers we are taking, which is bounded above, that will have definitely a greatest lower bound in R. So the axiom is precisely the following. So the axiom is every non-empty subset of R that is bounded above has a GLB or supremum in R. So according to this axiom, if A is a subset of R, A non-empty, A bounded above, then there exists S belongs to R such that S is equal to supremum of A. This is what the completeness axiom says. So three conditions it has to satisfy. It's a subset of R, it is bounded above, it is not empty. If all these conditions are satisfied, axiom of completeness guarantees that the set A will have a supremum in R. Just remember once again that supremum of a set need not exist in that set itself, but we need that supremum to be a real number. Therefore, supremum is going to be in R, not necessarily in A itself. Now, why do we say that this axiom makes R something special compared to Q? Just recall that we have already seen that square root of 2 is not a rational number. So, if we consider the following set, S is equal to the set of all x and q, rational number such that x squared less than 2, then this set is non-empty because 1 belongs to S and therefore S is not empty. And this set is bounded above in Q, bounded above in Q, and one obvious upper bound is 2 itself. But though we are not going to prove it right now, it becomes clear later that the upper bound of, the supremum of S is going to be equal to square root of 2, but square root of 2 is not there in Q. Square root of 2 is an irrational number that we have already proved. Therefore, Q contains non-empty set that are bounded above at the same time having no supremum in Q itself. Therefore, we say that Q is incomplete as far as the supremum property is considered, whereas R is complete. That's what makes R much more special compared to the set of rational numbers. Now we make a precise statement to detect or determine if a given number S is a supremum of a given set S or not, given set A or not. So the statement is the following, and we are going to state it as a lemma. Let S in R be an upper bound for a subset of R. Then the statement, the claim we are going to make is the following. Then S is the supremum of A if and only if for any epsilon greater than 0, there exists and A belongs to capital A such that S minus epsilon less than A. So what we are claiming here is that S can be an upper bound S of A can be the supremum if and only if for any choice of epsilon positive, we can find an A in capital A such that S minus epsilon is less than A. Or in other words, what we are saying is that is S minus epsilon is not an upper bound of A. This is precisely what we are saying. That S is an upper bound in such a way that if we slightly reduce S by a very small quantity, say by epsilon, then it will lose the property that it is an upper bound. Therefore, any number less than S is an upper S is not going to be an upper bound. That's what this lemma says. So we are going to prove this lemma. So we have to prove in two directions. One is that if S is the supremum of A, then we have to show that for given epsilon greater than 0, we must find an A in such a way that S minus epsilon is less than A. So in the first direction, assume that S is equal to supremum of A. Let epsilon greater than 0 be given, or we took such an epsilon. Now S minus epsilon, epsilon is positive, so S minus epsilon is less than S. That's very clear. What is the definition of supremum? According to the definition of supremum, supremum is the least upper bound. And since S minus epsilon is less than S, since S is the supremum and S minus epsilon less than S, S minus epsilon is not an upper bound for A. So what is simply saying that S minus epsilon is not an upper bound of A? That means that not every element in A is going to be less than or equal to S minus epsilon. That means that there is at least one element A that is going to be greater than S minus epsilon. Otherwise, if it's an upper bound, what happens is every element in A will be less than or equal to S minus epsilon. That is not true. Means that its negation is going to be true. What is the negation of saying that? So we have a statement where we are saying that S minus epsilon is not an upper bound. So when S minus epsilon will become an upper bound, S minus epsilon, S minus epsilon is an upper bound provided every A in A, capital A, will be less than or equal to S minus epsilon. This is not true. This is not true means that for some A, S minus epsilon must be less than that A. Greater than or equal to is not correct. That means that less than must be true. For all it is not correct. That means that for some it must be false. So there exists A in capital A such that S minus epsilon less than A. This is what precisely we wanted. Therefore, this is the condition that we wanted here. So in one direction, we establish what we claim. What about the second direction? We have to assume that for every epsilon greater than 0, if we can find A such that S minus epsilon is less than A, then we have to show that S is the supremum. So in direction 2, assume that S is an upper bound of A such that for a given epsilon greater than 0, we can find A in A such that S minus epsilon less than A. We have to prove that. We have to prove that S equal to supremum of A. This is what we have to prove. Given that for every epsilon greater than 0, we can find an A such that S minus epsilon is less than A. To show that S is a supremum, we have to show that any other upper bound B, if we choose, then S is going to be less than or equal to B. To show that S equal to supremum of A, choose B belongs to R, B, and upper bound of A. So we are choosing an upper bound B of A. we have to show that S is supremum, we have to show that S is less than or equal to B. So if S is not less than or equal to B, what is the other possibility? If not, then S is greater than B. So if S is greater than B, what about S minus B? S minus B is greater than 0. S is greater than B, therefore S minus B is greater than 0. So let epsilon equal to S minus B greater than 0. Therefore S minus B, S minus epsilon equal to S minus B equal to B. But according to our assumption, for given epsilon greater than 0, we can find A such that S minus epsilon is less than A. There exists A in capital A such that S minus epsilon less than A. But what is S minus epsilon here? Therefore, B less than A for some A in capital A. But what is B? B is an upper bound. Therefore, B has to be greater than or equal to every A. But B is an upper bound of A. Therefore, B greater than or equal to A for every choice of A in capital A. But here we are getting B to be less than A for some A in capital A. This is a contradiction. This is a contradiction to our assumption that B is an upper bound. So there must be something wrong that we have assumed. So what is that we assume wrong? All these things happen basically because we assume that S is greater than B. Therefore, S is not greater than B. Therefore, S not greater than B or S less than or equal to B. For whatever upper bound we choose, S is less than or equal to B. Therefore, S equal to supremum of A since the upper bound B is arbitrary. So we establish that if S is such that S minus epsilon less than A for some A for every epsilon we choose, then we get that S is the supremum of A. So we establish the statement in both the directions. Now, what can be an analogous statement for infimum? Maybe we can state something like this. So we will slightly modify this. S belongs to R, be a lower bound for A. S is the, instead of supremum, we will make it infimum of A if and only for every epsilon greater than 0 there exists A such that instead of S we will take L plus epsilon greater than A. So here the alternate statement in the case of the infimum or the greatest lower bound will be L belongs to R, be a lower bound for A, then L is the infimum of A if and only for any epsilon greater than 0. For every choice of epsilon greater than 0, we can find an A such that L plus epsilon is greater than A or L plus epsilon is not a lower bound. That's what precisely. So the question is to prove it yourself. So I'm leaving it for I'm leaving this as an exercise to you.